wonderful mix of people, really. But I think with these 13 participants, you could start if you wish.
Okay. So do you want me to put my first slide already? Or?
Yes. Yeah, sure. You can
Okay,
do that.
Share screen 2. Share. Okay.
Yep. Looks good.
Oh, good afternoon, everybody. I am Osmar Zaiane. I'm a professor in computing science. I've been a professor here for more than 20 years. I'm also the director of the Alberta Machine Intelligence Institute. And I'll be talking about AI and machine learning. So this lecture actually has 3 parts. Let me see. The first part will be, well, is today. I will talk about what is AI, the past and present. Thursday, we'll talk about the future and what we think about it in light of this AI. And in part 3, I will dive into machine learning, which is an important part of AI. So let me first try to demystify or remove some doubts about some misconceptions. It is largely believed that computer scientists and particularly AI specialists, like I'm working in AI, people assume that these people think that human intelligence is more or less solved and that machines will soon replace humans. Well, this is definitely not true, according to me, even though duplicating some form of intelligence equal or superior to ours is one day inevitable. It'll happen. So I believe it will happen, but I don't believe that it'll happen very soon. Human intelligence is more complex than we may think, and actually we realize it day after day. With new paradigms like deep learning, and I will talk about deep learning later on, we can make machines do amazing things, and these things may seem to be clever, but deep learning, which is currently stealing all the attention in AI, is still very limited compared to sentient human beings like us. Like an alien in Star Trek once said that humans are a ball of mostly water. I think we are balls of emotions. We have a lot of emotions, and our actions are not just dictated by our brains, but we also have hormones and a microbiome inside of guts, and they have a say in our behavior and how we make decisions. So it's not just the brain. We're not always rational. Let's say, yeah, we function in a smart and astute way compared to other animals. We reason. Well, some animals reason too. I believe if we do not self-destruct, because we are vicious, selfish animals, we will eventually manage to build and have a machine that is as intelligent as us, if not more intelligent than humans. But in my opinion, unless we have some major breakthroughs very soon that we are not foreseeing, we are still far from that moment in our future where we will have this machine that is smarter than us. So let's give you an example that we are not able to do today. Humor. If I tell you all humans are intelligent, but some are asymptomatic, that seems like a serious kind of question, statement, but it's a joke, obviously. It means that some people don't show symptoms of intelligence, like we say asymptomatic for the virus. So humor is one of these most sophisticated forms of human intelligence. It requires semantics, interpretation, knowledge, culture, and also the timing. You have to know when exactly to say a joke to make it into a joke. Computers don't understand humor and can't create or even recognize a joke. we often say that sarcasm is very, very hard for computers. It's actually hard for humans as well, because you need to have some background knowledge. This being said, we are making incredible strides in that direction. So as somebody who is in the field of AI, I can see and feel this acceleration in the progress we are making. We're making and contributing innovations on a daily basis. I mean, it's very difficult to follow all the papers that are published every day. But we are also discovering every day that and realizing that the human intelligence is very complex and way more sophisticated than we think. So let's start by, because I'll be talking about artificial intelligence, an intelligence that is artificial, it's not natural. I don't like that term. I prefer computational intelligence, an intelligence that is computed. It's not really artificial. It's real. It does something. But we always, what is intelligence? We don't necessarily have the same definition. So I'd like to hear from you guys. What do you think about intelligence? I'm trying to bring you up here so that I can see you. No, I can't. But anyways, I don't see the names. I can see.
Yeah, there are 14 people.
Who would like to volunteer to tell us what is intelligence according to you?
Can I give a go?
Yeah, go
Sure.
ahead.
Yeah.
Being able to acquire and use knowledge.
Acquire and use the knowledge. That's interesting. Okay. Any other definition? So it said acquire and use knowledge. That's very good. I like that.
So in the chat, Alec McDonald says ability to integrate large amounts of varied format data.
Is that what we do as humans?
That's
so.
what he
Sight,
says.
sound.
Yeah.
Yeah.
I don't see the chat open in front of me, so I can't.
Yeah.
Yeah, well, it's part of it, possibly. Yeah.
I think self-awareness is important, or like an autonomy of sort.
Self-awareness, that's a tough one. Yeah. So we are self-aware. Do animals have self-awareness?
Some do.
Some do. Yeah. I mean, it has been demonstrated. Dolphins recognize their reflection on mirrors and things like that. Yeah. Any other definition?
Maybe pattern recognition and the ability to work with incomplete data, so you can extrapolate between data points.
Pattern recognition. So recognizing patterns, whatever those patterns are. So patterns like in our daily life. And let me show you something here, and then we'll go back to definition of intelligence. So here I'm in a kitchen, and there's a dog. The dog is smelling something interesting, so it's possibly food. Identify where that smell is coming from. It's coming from that oven there. How do I get it? So the dog wants to get that food that smells good, but it's too high. He's going around thinking about a solution. He has possibly a solution here. He's pushing a tool called a chair. Now assessing, can I go up? No, not enough. I have to push it further. Okay, it's enough. I go up. Oh, I don't have enough momentum to get there. So there's an assessment of what's going on. Okay, second attempt. I'm not going to stop on the chair. Go directly up there. There you go. I'm getting closer. Yes, it's coming from the oven. How do I get it? It's inside. Yeah, oops. Okay, I have to push harder. There you go. Ooh, it's hot. How can I get it? It's hot. So the dog is assessing, has a problem and needs to solve it, and is assessing the situation and finding solutions. Too hot, dumping it on the floor, and now I'm gonna go and get it and eat it. So the dog managed to solve a problem. It's not in the dog's world, natural world, it's in another world. There are chairs and ovens and managed to solve it by itself. Maybe that's a big animal. Let's take a smaller animal. Oops, no, that's not what I want. I'm going to stop this. Here, there's a roof, some snow, and if I zoom in, I can see a crow. And the crow sliding on the snow. Well, it's not just snow. He has a lid, a plastic lid, that he climbs on and tries to slide, like we do. No, it doesn't slide easily on rust. It doesn't work that way, especially if there's a blockage there. So you'll take the lid, move back to where it experienced it before, and it'll do it again. Yahoo! So this crow is not trying to survive. It's not trying to eat or protect itself. It's just having fun. It's having fun. Okay, maybe that's also a big animal. Let's go with something smaller. Do you know what that is? Any idea? It's a rope? Well, actually not. This is quite interesting. It's a bridge. It's an ant's bridge. It's an army of ants that build a bridge to attack a nest of wasps, a wasp's nest. So they together hold hands somehow and build this incredible bridge. I mean, how to do it is phenomenal. We still don't understand how they come up with this. This is one form of intelligence, swarm intelligence, we call it. It's a swarm of ants. And they build this bridge. Actually, it's amazing how to do it in the air to attack this nest of wasps and get the eggs out. Are these forms of intelligence? So I'm going back to you guys. Anybody else wants to volunteer a definition? Or not a formal definition, but what do you think is intelligence? What is intelligence? Is this intelligence?
So Charlie Wang says ability to make accurate predictions about the future. And Boyce says ability to put knowledge into application and actions. Anka Chan says ability to reason and make decisions through integrating emotions and logic. Thomas Banks says ants as well, which is surprising. And Alec McDonald says sophisticated sentience. How about that? Yeah, that's almost poetic, man. Yeah.
I mean, accurate predictions. This is cool, and this is probably somebody who looked at reinforcement learning, because that's what we do in reinforcement learning. The ability to reason. Yes, these are great, great attempts anyway. So actually, it's tough. Intelligence is defined in many ways, but there's no standard definition. In psychology, there are theories of intelligence. Some researchers have suggested that intelligence is a single general ability, like we humans have that, who maybe don't have it, I guess. But others believe that intelligence encompasses a range of aptitudes, skills, and talents. For example, the capacity of learning from experience. But we don't just learn from experience. We humans can also acquire knowledge from teaching. I can tell somebody, hey, don't touch that candle when there's fire because you'll burn your finger. Well, some kids will not listen and will put their finger there on the flame and then feel the heat Then they will learn from that experience. They will not touch it again. While others will say, yes, mom, or yes, dad, I will not touch it. So they build that kind of representation of that knowledge and acquire it and put it in their model. So the capacity of learning is part of intelligence. The ability to recognize and understand problems, like that dog that we saw there. I have a problem. I have to get to that food. I know there's food there. I can smell it. But how do I get there? I'm too short. The capacity of reasoning, planning, and solving problems with the tools at hand and in the environment we are in. So that dog found the tools, the chair, planned to push it first and then climb and then go to the oven, then open it. So that's planning. And there's a kind of reasoning to adjust all these together. The capacity to change our environment, the environment we're in. So it's like, changing the environment in our own advantage to the betterment of our condition. So the capacity to adapt to that environment. Also the capacity of understanding and expressing emotions. Some people talk about emotionally intelligent. Some people are emotionally intelligent, more intelligent than others. So you see, it's complicated, and we're still debating this, and we're still learning from that. Yet, we're talking about artificial intelligence, and I'll get to that. So today we'll talk about what is artificial intelligence, what is machine learning, and why now. Actually, it's not now, it's old, but it's coming back in a big wave. And then I'll show you some examples. So artificial intelligence, and we'll get to the definition, started in the 50s. So in the 50s, there were people, scientists, who were thinking about, okay, now the war is over, the Second World War is over, and we have these machines that we built for calculating trajectories of missiles and deciphering the code of the enemy. What can we do with these machines? And some people started thinking about, hey, if these machines can solve some small problems, and if we can break down the human intelligence into small tasks, and each task can be coded and can be solved individually, we can put them all together and we can create a machine that is intelligent. That's the artificial intelligence. And they coined that term in 1956, so it's quite old, more than half a century. And they argued about that, and then finally they convinced funders, and at that time it was the government. And the government, don't forget that in the 50s, that was the Cold War, and that's when they started the race to go to the moon and so forth. The Russians wanted to show that they're better than the Americans better than the Russians. So if we can build a machine that can think, that'll be fantastic. So there was a lot of hype around this new thing called artificial intelligence. And to prove it, people started working on tasks that we do that we all agree require some kind of intelligence, like playing chess. Oh, you have to be intelligent to play chess and win. So the people who were masters, we consider them very smart and very intelligent. So a lot of that effort in the beginning was about imitating the human intelligence via these surrogate tasks. So these games, for example, there's a lot of expectation, was a lot of money invested by governments, not just in North America, but in Europe and also in the Eastern Bloc. But after a while, there was a disillusionment. People realized, this AI thing cannot deliver on the promises, especially after the paper by Dreyfus said this is a utopia, it will never happen. So there was a, well, after this disillusionment, what happened is that the funding dried out, of course, but some people continued, not just tried to mimic human intelligence, but they tried to focus on very specific tasks within AI. And it's in the 80s that a subfield in AI called machine learning showed some interesting success in some applications. So machine learning, and we'll get we'll get to it. So it's a subfield within AI. And now we have it everywhere. Machine learning, it's ubiquitous, and we don't even realize we are using it in our phones, in our televisions, in our distributor of cash and banks and whatever. Everywhere there's machine learning. So one example here I'm showing is detecting which email contains spam and which email is actually useful for me, and I can automatically put it in the spam folder. It had some success in some applications, but not enough to create the same interest that we have today. So what happened is that it brought back some hope indeed, and people saying, oh, okay, so it is useful to some things, but it's not as exciting. It's only lately in around 2012, actually, to be more exact, there's a new subfield within machine learning. So it is also subfield of AI, obviously, called deep learning. And deep learning it's hinging on technology. That's actually a rebranding of technology that existed before called artificial intelligence neural networks, or artificial neural networks, sorry, to be more exact. It's a simulation of how we thought at that time in the 50s, how the brain functions. We still don't know how the brain functions. We're still learning. But they're simulating how neurons communicate, and they can build a model. I'll talk about it later, how this model can learn things from training data and can do amazing things, even better than humans. And I'll show you some examples later. So the big picture is that we have this field of computer science. In computer science, you have the field of artificial intelligence. So artificial intelligence now, well, it's a field that started in the 50s, and now it's taught in every single university, every single school that teaches computer science. There is a course of artificial intelligence as part of it. But it's as important as any other subfield in computer science, like database management systems, security, encryption, algorithms, human-computer interaction, networking, high-performance computing, and so forth. I made it bigger here because I'm going to zoom, but it doesn't mean that it is the most important subfield of computing science. Within AI, we have what we call machine learning, as I said, but it's as important as other fields, subfields in AI, like planning, knowledge representation, reasoning, and we mentioned that in the definition of intelligence, so planning and reasoning. There's also computer vision, natural language processing. These are all subfields within AI. And again, I put machine learning in a big circle, not because it is the most important one, it's only because I'm going to zoom in. So within machine learning, there's what we call supervised learning, there is unsupervised learning, there's reinforcement learning, there's so different ways of learning. So what you should remember from that is that computer science has AI inside it, AI has machine learning inside it, machine learning has supervised learning inside it, which has one of the paradigms called deep learning. The reason I'm showing this figure and talking about this, it's because in many places, in many newspapers, many magazines, they're still talking about deep learning like if it was synonym to AI, but AI is way more than just deep learning. So deep learning is one technique, let's say, of supervised learning within AI. Okay. So yeah, so this is what you need to remember. Deep learning is machine learning is AI. Okay, let's go to an artificial, since we're talking about artificial intelligence, here's an artificial brain, and try to understand what is AI. I haven't defined it yet. So some people are talking about AI. Well, AI is so important, the market will be worth $60 billion by 2025. So obviously, if I give you a number like that, actually that has been revised and it's even bigger. That tells you AI is very, very important. And I don't care about the definition anymore. I know it's important in my life. Well, that's wrong attitude. We should actually try to define it. Somebody said, the one who dominates AI will rule the world. Any ideas who said that? No? Well, it's a very famous guy who said that. And it's a guy who is also ruling a big part of the world and trying to rule the rest of the world. Like many of the rulers of the world, they try to dominate the world. This is Putin. Putin said the one who dominates AI will rule the world. And he's not completely wrong. He's actually right in that that is one of the reasons many governments are investing heavily in AI, because they don't want to be left behind. So often the definition that we get of AI comes from magazines and newspapers. Unfortunately, those journalists reporting on technology, so we think they are actually, they know what they talk about. Often actually they don't know what they are talking about. And they're looking for sensational stories, scoops, before even they happen. So where should we get our definitions? Well, many people would get their definitions from science fiction movies. Movies are just the imagination of script writers and film directors. Interestingly, however, often they are more accurate than many science foretellers. But movies and the media in general, they portray an unrealistic picture, often pessimistic, of AI, like them against us, the evil against we, the kind humans. And so the AI is our enemy. Which is definitely not the case. If you want to know what is AI today, what's the level of AI we have, well, look at in your pocket. Your cell phone is actually the best illustration of what kind of AI we have today. The speech recognition, speech to text when you dictate something, the fact that it recognizes your preferences, the fact that it predicts the words as you type them, all that is the AI we use today. So what is AI? Well, definitely not the movies. One of the pioneers of AI, he was in the first meeting in 1956 when they defined artificial intelligence. Marvin Minsky, he's the founder, who was the founder because he died 2 years ago, I believe. He was the founder of the first AI lab in the world at MIT. And he said artificial intelligence is the science of making machines do things that would require intelligence if done by men or by humans. So he piggybacked on the definition of intelligence. He didn't even define what is intelligence, but as long as it requires the intelligence that we have as humans, then if it exhibits that, then yeah, the machine is intelligent. So in other words, artificial intelligence is discipline now. It's a science, striving to get machines to behave intelligently by performing tasks that would normally require human level intelligence. For me, artificial intelligence is an enhancement of the human creativity. We build new tools, basically, and AI is one of the tools. I'm building AI to build more sophisticated tools so I can do things that I wasn't able to do before, or whatever I was able to do before, now I'm doing it better. Okay. And artificial intelligence per se is actually a moving target. What we called artificial intelligence before, I hope this stops, there you go. What we used to call artificial intelligence before is definitely not today. And what we call today artificial intelligence, maybe tomorrow will be, take it for granted, it's not artificial intelligence anymore. I don't know if you, well, probably you take it for granted as well. A word processor. A word processor, well, I lived the time when we shifted from typewriters to word processors, and people were saying a word processor is artificial intelligence. It's amazingly, I mean, it's capable of doing things that we are not able to do with a typewriter. For example, automatically justifying a text, finding mistakes, correcting mistakes, being able to correct mistakes, things that obviously were unimaginable with a typewriter. I mean, to justify text to the right, to the left, or to the middle, or justifying completely the line by line was a very hard task to do. Who thinks a word processor is artificial intelligence today? Nobody. I mean, it's a trivial thing. Okay, so it's a moving target. There's another term that often we associate with AI, and actually it was very prominent before. All the hype was on data mining before. Now somehow some people encompass it within AI, but they're two different fields. They overlap quite a bit. It's data mining. So what is data mining? Data mining is a process that is part of a bigger loop, let's say, we call it knowledge discovery. So data mining is a process of discovering and extracting potentially useful and previously unknown patterns from large collections of data. So you have a lot of data and somehow you extract something that, some regularities, some formulas, some rules, some patterns that are hopefully useful and they're new. That's why we call it discovery. So it's the analysis and interpretation, intelligent interpretation of large data in order to provide actionable knowledge from this data for human decision support or for another process that is automatic. And we will see that machine learning, because it's also trying to find patterns in the data in order to help some kind of prediction down the road, it follows the same pattern. It's also data mining. But not everything in machine learning is data mining, and not everything in data mining is machine learning. Actually, data mining is at the confluence of many different subfields. Data mining has database management systems, has part of AI, has visualization, statistics, high performance computing, information retrieval. And so data mining is right in the middle there. What is data science? That's another buzzword. It's a multidisciplinary field that uses processes and algorithms to extract also knowledge and insights from data. It deals with the problems of storing such large data and moving such large data and accessing it properly, because that has many technical challenges as well as the management. So the question of infrastructure is built in the data science, but as you can imagine, data mining is part of it. So if I draw it this way, you have databases, you have statistics, you have computer science, and you can see here data mining, you can see machine learning, which is part of AI, and data science is right in the middle of all these intersections. But it deals also with management of this large collection of data, often distributed in different places, and you have to bring it and aggregate it and so forth. So often these terms are synonymous. So data mining, data analytics, big data, data science, business intelligence, to the point that we are all confused and we don't know what is AI, what is machine learning, what is big data. And so let's go back to AI. As I said, AI is not new. It started in the 50s. And now it's coming back. Why is it? Why is it that there's this very important resurgence, huge investment, this time not just from governments, governments, you look at China, they're investing billions of dollars in AI, but many companies, so private companies are investing a lot of money in this field. Well, there are three reasons why AI is coming back full speed now. And there are three factors that play a huge role. One is the incredible availability of data. We have a lot of data. We collect data all the time. As you walk, there's data collected about you. Your cell phone is checking the satellite, the GPS to see where you are. You're searching online, you're browsing, whatever. You go to the hospital, you start your car. We are collecting. It's incredible what we do. You take a picture. In addition, our computers have evolved significantly. In the early days of the AI field, the computers were ridiculously slow, didn't have large capacitive memory and so forth. So even some interesting ideas that they had in the 50s, well, they could not implement them to see whether it works or not. The third factor are these new algorithms. So we have new algorithms that now we can dare trying and testing because we have the data and because we have the infrastructure. So let's dive in some of these, actually the three of them. First of all, where's this data coming from? Well, obviously, when you go online, you have a lot, anything you do online is collecting a lot of data. A number of emails, every second we have 3 million emails, tweets, 50 million tweets a day, Flickr, how many images every minute are uploaded, how many YouTube videos are uploaded. It's phenomenal. All that data is used for different activities. Some people actually measured this and they studied it. There's a paper that talks about, well, they tried to do the analogy. When you talk about, like, for example, they say in 2011, there was this paper that talks about the US healthcare system. The US, well, this is I was going to say the Internet of Things, the healthcare, the electronic medical record, the insurance providers, clinical trials, genome data, and so forth, the social media. There's a lot of data. But anyways, there's a paper that talks about the healthcare system in the US collecting about 150 exabytes of data. What is an exabyte? Well, 1 exabyte is equal to 1 billion gigabytes. So we know what a gigabyte today is as part of our jargon. Well, an exabyte is a billion of these gigabytes. And the paper was trying to actually estimate how the growth will take us to, I mean, a different dimension, zettabytes and yottabytes. Zettabyte is 10 to 21, so 21 zeros, a 10 with a 1 and then 21 zeros after that. These are actually our minds cannot fully grasp anything of that scale. It's very, very, very big. So we have a lot of data, more data than we can handle anyways. So because these are big numbers and we can't really grasp it, some of these papers were trying to making analogies. So one paper that came out in 2011, I think it's the same one that I'm talking about here, looked at the data in 2007. Even though the paper came in 2011, they did the analysis in 2007, and they said if we take all this data, the photographs that we have, the medical images, the text that we enter, all the stuff that we are collecting, and we store them in CDs. I don't know if you remember CDs, compact discs. Nobody talks about CDs anymore, not even for music. So if you put them in CDs and then you stack them one on top of the other, and knowing that a CD is 1.2 millimeter, then you will need as many CDs to create a tower that reaches the moon. That gives you an idea how much data we are collecting. But forget the CDs and forget all the data. Just focus on, this is a year or two later, which is interesting how fast this is. This illustrates the speed at which this is growing. There's another paper that talks about just medical data. If I look at just medical data and forget all the other data and forget the CDs, let's put them on DVDs, and nobody talks about DVDs anymore, but that's what they did at that time. And they did the same calculation with 1.2 millimeter thickness, and they showed that you can go to the moon twice. You can build 2 towers from Earth to the moon just with DVDs, with data just from medical data. So this illustrates the phenomenal quantity of data that we are collecting. How are we storing it? Well, now nobody talks about CDs and DVDs, of course, but if you look at the capacity of storage that we have, and this is 2005, putting it on a micro SD card, very tiny space. In that tiny space, 10 years later, we are not talking about megabytes anymore, we're talking about gigabytes. And then in 2 years, we doubled it. Actually, today you can buy more than a terabyte in the same space. So we can cram more and more data. We went from 128 megs to 124 gigabytes. That's what a terabyte is. So an improvement in 14 years, 8,000 times. So 8,000 times improvement. That's phenomenal. and these are cheap. They're becoming cheaper and cheaper. I don't know if you've seen this picture. This picture was taken in 1956 because IBM was selling a hard drive, it's 5 meg hard drive, 5 megs. Yes, 5 megs. So the size of a high resolution picture, one picture. But at that time it was a big deal, such a big deal that the captain of the plane, Pan Am, was there attending the event for a photo op. And the price of that 5 meg was at that time $120,000 for 5 megs. Well, today you can go online, you can buy this. I didn't update it because this is the last time I bought an SD card, 64 gigabytes for $18. So that means that 64 gigabyte SD card, if I was able to travel back in time in 1956, it would cost $1 billion. $1 billion on your finger. That's insane. $1.5 billion, $1.5 billion. So there's an improvement in 62 years, as well as quite a bit of time though from 1956, but still it's an improvement of 76 million times in terms of price. This is just to say that there was an incredible improvement on this dimension, the dimension of data. We collect a lot of data because it's cheap to store it, so we store everything. We don't even think about space nowadays because it's free, basically free. So the other dimension is this high performance computing, and just to give you an idea here, you can buy a GPU today for less than $1,000. GPUs are to accelerate the rendering on the screen. Many people using it for games, so that you can have a high, a lot of frames that you can. You don't want your CPU to do all these calculations. This is a special card specifically for the calculations to render things on the screen, and that GPU is becoming actually more powerful than the CPU itself nowadays because of the push from the gaming industry. There's a huge demand. But what you can buy for $1,000 is equivalent to the Cray 1 supercomputer that when it came out, this Cray 1, actually it was embargoed on many countries. The United States, when they didn't allow the company to sell it to some other countries. Now anybody can buy it and put it on a commodity computer and run it at home. This shows the incredible progress. Actually, there's some people who are tracking this progress of the fastest machine in the world. This is in the last a few years. I think they started in 1993 or 92. Here you have a figure of the fastest machine in the world. This is what you see in the golden triangle. You can see that this is a logarithmic scale. Here you have the years, and it's a logarithmic scale, so it's increasing very, very fast. And a few years ago, and for many years, the Chinese had the fastest machine. They were counted the speed was counted in petaflops. So how many operations, floating point operations it can do in a second, and peta is basically 10 to the 15, so 1 billion operations. For a long time, as I said, it was the Chinese who had the fastest machine, and then finally IBM built a machine in 1918 with just GPUs, actually a lot of GPUs put together, and they reached 122 petaflops. And actually they managed to crank it up to 200 petaflops, which is amazing last year. And just when they reached 200 petaflops, the Japanese came up with the fastest machine last year in June, and just in time to work on the COVID pandemic. And they reached 400 petaflops. So the interesting thing, and this is, so indeed this incredible improvement, but the interesting thing is if you compare these machines, the Japanese one has 7 million CPU cores. So when you buy a machine that typically they tell you is a quad core, so that 4 cores on the CPU, this is 7.3 million cores, huge. The American computer from IBM was 203,000 CPU cores, and they had also 27 GPUs. So what is interesting is looking at the power they use. So this incredible machine was using 13 megawatts. So it's like almost like a town. The Japanese one, 28 megawatts. So it's increasing. Now compare it to a human brain. A human brain has 90 billion neurons. We're not talking about million CPUs here, 90 billion neurons, and it uses just 12 watts. So all that reasoning that we do in the planning and the learning, and 12 watts is just a small, tiny LED light. That puts it to scale. Okay, so anyways, the point I wanted to make is, well, I said before that if you want to see the AI, look in your pocket, and that phone has actually, it's the incarnation of all the AI that we have today. Look at the most powerful cell phones we have today. This, I didn't update it. This is from 2018, the iPhone X and the Samsung S9. If we want to compare these cell phones that we have in our pockets to these very big machines, well, you'll place them here. The best, fastest cell phone is around 1 teraflops, and it is equivalent to the fastest machine in 1996, so to 97, to almost in the fall of 97. That machine was 10,000 Pentium Pro processors. It was equivalent to a tennis court in size and used 850 kilowatts. It was enough, so to give you an idea, what is 850 kilowatts? We're not talking about megawatts like the current machines. That is enough to basically give energy to 800 houses, so a big town. And the cost of that machine was $55 million. Well, today, that's equivalent to a cell phone. So this is the big machine, and you have it in your pocket. That's the cell phone you have in your pocket. That gives you an idea about the progress we made. It's phenomenal. Okay, that's your phone there. So if I look at the progress from here now, the more or less the fastest machine last year anyway, the year before, and this actually the machine in this scale here is the one in 1993 when I started my PhD. The increase, the improvement in terms of number of operations that it does per second, I told you this is a logarithmic scale, it's equivalent to 206,000 times in 25 years. In 25 years, the machines have improved by 200,000 times. What does that mean? Just to understand what that means. So if I was able to evolve as fast as these machines in 25 years, when I did my PhD, that means that if I was doing 1 step is equal to 1 meter, today my step will be 206,000 times a meter. What does that mean? That's 206 kilometers. So today I should be able, with 1 step, I should be able to go anywhere in the circle. It's crazy when you think about it, but that's exactly the progress that these computers have done. Okay, and if I do the same analogy, the progress that we did in how much data we can cram in the same space, I said we increased it by 8,000 times. It's like being able to do 8 kilometers in each step. Okay, and if I look at what is the 76 million times increase, well, it's like with 1 step I can go around the Earth twice. So that shows you how much we improved in terms of capacity of computing, and these are the early days when people were talking about AI. I mean, this is ENIAC in 1946. These are the computers at the end of the Second World War. This is the Zeus, the German computer. They were talking about 385 multiplications per second. We're not talking about petaflops here. And the computer that was used for calculating like trajectories of missiles and things like that, they were doing 1,000 floating point arithmetic operations in an hour. Okay, we tend to forget it, and we tend to take things for granted. We have a cell phone in my pocket, and yeah, but hey, yesterday it wasn't the same. Okay, so this is what made AI possible today, because we have these computers, incredible memory, incredible computing power, and a lot of data. But there's another thing in the equation, which is the algorithms. In the algorithms, we did incredible improvements as well. Among them, I mentioned deep learning. So what is deep learning? Deep learning is basically an old technology that was suggested already in the 50s. They are trying to simulate the cells in the brain, so a neuron, and they connect them by layers. So one neuron has some input and has some output. The output, these are connections. So each neuron is a node, and you connect these nodes by layers. So here's a zoom on one neuron, artificial neuron. So you have input coming in with different weights. We call it a vector. And then you have here a decision, should I fire or not? So there's what we call an activation function. And that activation function will say, okay, fire now, message going forward. And that message going forward goes to the next layer. The difference is that this idea, the difference between before and today, this idea was not able to be implemented with the computers that we had in the past, but because we have a lot of memory and a lot of power, now we can put them in many, many, many layers, and that's why we call it deep learning. Okay, the way it learns, I will cover it on the third lecture, but basically it learns weights in these connections. There's some algorithms also to learn connections and remove connections, but in general, the connections are already established, and you have a particular architecture and you learn these weights. There are different architectures that exist. There's what we call convolutional neural networks, recurrent neural networks. There's also, we talk about LSTMs and things like that. That's not relevant here. The interesting thing, however, is that, as I said, this is an old technology, and when people lost interest in machine learning and the funding was gone, there were some people who persisted in working on some aspects of AI. One of them is neural networks, and also neural networks was not even when people continue to work on machine learning and AI, neural networks were not the sexy kind of topic, and was ignored and forgotten by most, except some stubborn people who kept on working on that. And some of them are in Canada. They're considered today as the fathers of deep learning. There's Joshua Bengio from Montreal and Jeff Hinton from the University of Toronto. And they demonstrated, I'll tell the story later on, they demonstrated that this actually can do amazing stuff. There are other people as well, like Yann Lequin, actually in French. He's a French guy. He's now the head of AI at Facebook. There's Jürgen Schmidhuber as well, and a German guy in Switzerland who also worked on basically reviving the neural networks in this new subfield, deep learning. So what's the story behind this? This is actually quite interesting as well. There is a competition for recognizing what's on a picture. So we call it image classification. So there's 14 million images with different labels. This has a plant, this has an animal, this has a building, this has a person, this has a piece of food. And people were building algorithms to recognize them automatically. And this competition started in 2009. And every year they compete again with new techniques. And you can see there's some kind of improvement. This is the accuracy. How accurate are their classifiers? It was going up in a reasonable way because, well, there are new techniques. And then suddenly in 2012, some guy, a team from, actually a team of 2 students and their supervisor, this is Jeff Hinton, participated in the competition with something new, and they used GPUs, and it jumped suddenly up here to the 80% accuracy. You have to understand that the humans also, when they look at these images, they make mistakes. And typically they are in the 80s here, and very expert person, very familiar with this data set, maybe reaching the 90s, 90 something percent. And so this big jump was very surprising. And people went to the winners and asked them, so what are you using? What did you use new that gave you that big boost? And they said, well, we use neural networks. We call them now deep learning. And that's when people suddenly got interest in this new technology. And it became very successful because the team of the two students and Jeff Hinton were invited to implement this with Google, and Google having all these images from the web. They had a lot of data, and they implemented for their images to recognize cats and dogs, and was incredibly successful. They were interested because they can index now these images with words, not just with colors and stuff like that. And there's another competition. They say, oh, since you are very successful with images, let's try it on another data set that is very hard. There's a data set, a switchboard data set. This is data of, there were recordings of people talking on the phone. And DARPA started this competition in the 90s, asking people, can you transcribe this speech into text? Because it's easier to analyze the text than listening for hours and hours of what people are saying on the phone. So for many, many years, people were working on this. So this curve is different. This is the error rate. So the lower, the better. And you can see that for many, many years, they stayed in the same kind of range. And then when we started using deep learning, it now is doing better than the humans at transcribing voice into text. So they tried it on other things like detecting objects and images. And again, we do better than humans. There's translation. It's not better than humans, but there's a huge boost thanks to deep learning. Tried it on visual question answering. You show a picture and you ask questions about it. There's also a text comprehension. There are different tests. And you can see it's not reaching the human performance like here, but it's going up and soon it'll surpass it. So you think, wow, this is amazing technology that is really competing with humans on many of these intelligent tasks, let's say. But there are some surprises. So what do you see here, for example? What do you see here? Who can tell me what you have on your screen?
A desert.
A desert, yes. What else? Do you see dunes? Dunes of sand? Yeah, nobody's, I don't know if you guys are connected, not connected. You're listening, not listening.
People are saying sand dunes in the chat, so.
Sand dunes, yes. But this image was given to a program that the British police is using. So the British cops have a program to try to find pedophiles and people trafficking with porn. So they look automatically to the images that are exchanged and they try to identify the bad ones. This one was labeled as a picture of nudes. Okay, so obviously not nudes here in the dunes. What about this? What do you see here? I've never seen this in my life, except in the picture. Have you seen this before? Do you know what it is? So you haven't seen it before, possibly, but you will recognize it immediately, wouldn't you? What is it?
Ferrari.
It's a Ferrari. Okay, so what does Ferrari do?
It's a car. It's rear end.
Cars, yeah, exactly. You notice a car, but you don't see the wheels. You don't see, this is not normal lights and not normal windshield, even though it has this bizarre look. I mean, I could say these are eyes of an insect or something, and these are teeth with funny nose here with 3 nostrils or something like that. If you give it to a deep learning model that learned on images of animals and things like that, and cars and plants, it will tell you it's a horse. Why is it a horse? Well, there's a horse there and the logo. Okay, so let's turn this car so that I can see the wheels at least and a door and things like that, things that I recognize in a normal car. Here, I turn it. Maybe deep learning will recognize this car. If I give it to deep learning, it will not say a car. It will say horses, because I see a horse here, but I see other horses there too. Okay, so it's not perfect. Let's see other examples where deep learning is trying to describe an image, not just say, label it as a car or a dog or a horse. So here are examples. You look at this picture, and then the description by the deep learning model says a soccer player is kicking a soccer ball. It's not bad, but I don't see the action of kicking here. He's just standing next to the ball. So this shows you the importance of the kind of training you give to the deep learning. Here it says that a street sign on a pole in front of the building. So it's very descriptive here. You have street signs on a pole in front of the building. Actually, we humans can actually say better than that, say something better than that, because it's not necessarily in front of the building. It can be on the other side of the street, given the size of the scale of these windows and the depth. We can estimate the depth between the pole and the wall. So it's not really correct. And here's another example with the depth. Here it says a couple of giraffes standing next to each other. Are they standing next to each other? Look at this one small. Look at where the floor, the bottom of this one is here, the bottom of this one is here. So you can estimate some kind of depth. And obviously they're not next to each other. It's not that bad. It recognized giraffes. It recognized it as standing, but it is still not perfect. Let's see another example to show you that actually it's sometimes difficult for humans too. Are these puppies or bagels? I can tell you the deep learning models we have will have trouble with these unless you train them specifically for this case. Here's another case. Is this a Chihuahua or is it a muffin? No, well, some of them are really hard, really. Look at this one here. And sometimes if you put in the picture, the Chihuahua and the muffin, then it's harder. Which one is which? And there are many examples like that. Here, what is this one? What about that one? Actually, there is now a field where we're trying to trick the deep learning to recognize something that is not what it sees. And this is by adding noise to images. Some noise that, so random noise that we cannot see. Like for example, in this case, this is a panda and this is a gibbon, and you can train the deep learning to recognize both. But here's a panda again, and the deep learning says, well, it's a panda, and I'm confident 57%. Okay, I have a 57% confidence that it's a panda. It doesn't see the whole panda, it just sees the face and part of the body. Now, if I take that image and I add this random noise on top of it, suddenly, well, for humans, we don't see the noise, but the computer now confuses this, the deep learning confuses this with a gibbon, and it's way more confident. And 99% it's a gibbon, because now it's focusing just on the face, and the face looks like a gibbon. Here are other examples. I have a banana here, okay, and the deep learning says, well, I recognize a banana, and this is my confidence for the banana. It may be a slug as well, but it's very low confidence. It may be a snail, very, very low confidence. Maybe an orange with very, very low confidence, but I'm very confident it's a banana. And then I take this funny thing that looks like a cell. It's an artificial kind of thing, like a Golgi apparatus and all the things here, and I put it here, superposed with the image. And suddenly the deep learning, instead of focusing on the banana, it says it's a banana, but I'm not very confident it's a banana, but I'm very confident it's a toaster. It's not even a toaster, but it thinks it's a toaster. So you can fool these deep learning models quite easily, and there are many people working on that. Okay, so it's not as beautiful and as nice as you think. So deep learning, as I said, is part of, I have to be careful with time. Please remind me, Dr. Solis, because I'm not, you know me, I talk too much. So deep learning is part of a subfield, as I said, that we call machine learning. So what is this machine learning? So machine learning is actually trying to learn a representation. I will not go on that path. I'll define it differently. Machine learning provides means to machine programs to learn from some data, interpret it somehow, in order to be able to adapt to that data. So machine learning is basically learning from experience. The data that we give it is the experience, and we learn to predict. To predict why? To adapt to the environment. The environment is changing, and I can adapt to it. So in the field of machine learning, you have deep learning, but you have other paradigms like support vector machines, like associative classifiers, and so forth. They require, in the supervised learning, they require some training data. I have to give it data that is labeled, and it learns from that. So here's how I show it in an image. So you have data that is labeled, and the algorithm goes over it and builds a classification model. So this is a representation of what it learns to discriminate between these different classes. I represent the classes here by colors, and later I will have other objects that haven't been labeled. They don't have a color here. And basically I will use this model, this cloud, I'm representing here as a cloud, I'll use it to automatically predict what is the label for these new objects. So this cloud here could be a neural network. Okay, it could be a neural, but it can be other things. It can be a hyperplane crossing the space like an SVM or other things. Okay, so that's what supervised learning is. I give a supervision here by providing a training data. I learn a model that represents somehow a discrimination between these classes, and I will use it to predict the labels of new objects that haven't been seen before. There are other paradigms as well, like reinforcement learning. Reinforcement learning, which we are known for here at U of A worldwide. It's a completely different idea. The idea is that we try, so trial and error, we try things until it succeeds, and we get a reward that tells us, yes, you did very well, and I learn by trying to maximize the reward that I do. So what I learn basically a policy that tells me what actions to take. I think I have a slide for that. But before I talk about that slide, I want to go back to deep learning and why deep learning is very interesting these days, even though it coexists with many other machine learning techniques, because of this particular observation. So this is the performance. This is measuring the performance, how good I'm getting. And this is the amount of data that I have available for training. The typical algorithms for machine learning that we have been using for years, since the 80s, they learn. The more data you give it, the better it gets. So the performance gets better. And then at one point it plateaus. It's like it doesn't know what to do with more data. However, for deep learning, beyond a certain level where the old algorithms cannot improve, deep learning continues to improve. The more data you give it, the better it gets. And that's why at one point, it does better than even the humans. So we have applications that you're using today and you don't realize that they have machine learning involved in them, like spam detection. If you use Gmail, it looks at your behavior, what you delete, what you read, what you save, and will give it more importance. So there's this notion of important email, starred email, and spam email. It's basically your actions are the labels that you give to the machine learning behind the scene, and it learns what is considered as spam for you. Because what is spam for you may not be spam for somebody else. And what is spam for somebody else may not be spam for you. It may be interesting for you. Another application that is very common is the credit approval. When you go to the bank and you ask for a loan, well, they look at your file, your characteristics. Do you own a house? Do you have a job? How old are you? What kind of diploma do you have? And all those characteristics will be fed to a machine learning model that has learned on previous data with other characteristics and whether they actually paid back the loan or not. So we can predict, based on your characteristics, what is the probability that you will pay back or default on your credit, and then they will use that to approve or not approve your loan. When you use your credit card and swipe your card, there's an authorization that goes, or a request for authorization that goes to a central computer, and the central computer will, before sending the authorization back, will check whether there is any possible fraud based on your previous purchasing behavior. So it learns from your past to recognize what is unusual, and this is using machine learning. There are many examples in precision health, also using, I don't know if today I will use examples or maybe next time, to do diagnosis, prognosis, treatment recommendation, and so forth, using machine learning. Another example where, I mean, the sky is the limit for applications in machine learning, but this is an example to show you how far-fetched it can be. This is an example of a paraplegic. Well, this student is not a paraplegic, but the student is simulating a paraplegic. He's not doing anything with the chair except thinking. So the patient has a helmet with sensors, and it can detect the ECG, and you can control your wheel to move forward, backward, stop, turn left, or turn right. How? Well, we train it, we give it labeled data to train on things like what happens, what is the activity in my brain when I think about moving my left toe, for example. And then we associate that left toe, when we detect that the person is thinking about moving the left toe. They can't move the left toe, they are paraplegic, but just thinking about moving the left toe, I should turn left. If I'm thinking about my wrist, doing a fist, for example, then that means stopping. So we train a model to recognize these activities in the brain when I try to do some of these actions that I can't do, but just thinking about them, then I can control, a paraplegic can control the chair automatically to move forward, backwards, left, and right. So this shows you how, I mean, the kind of applications, are incredible applications that we can do with machine learning. The same thing we can do also with moving a cursor on the screen, left, right, up, down, and select letters. So there is a user interface that is based on the same kind of bonnet that you can put on your head with these sensors in order to write. So these paraplegic cannot use their fingers to write, but then suddenly they have, thanks to machine learning, they have incredible interfaces. So I mentioned reinforcement learning. I better give you a little bit more information about it. It's different than the previous one. There is a notion of experience, but the experience is not these labeled data that is given to you for supervision. So in reinforcement learning, there is what we call an agent that is trying to learn, and then we have an environment in which they live, they evolve. The agent will choose an action among different actions that are possible, and the environment will change, and so the state of the environment will change, and there's a reward giving them basically a kind of feedback saying you did well or you didn't do well. This is what we call the experience. So again, so imagine the agent is a robot, but it doesn't have to be a robot, but and robotics is one of the most prominent application for reinforcement learning. It's not the only one. You have the environment here, it can be a maze or tool, things, like whatever. The agent has at its disposal a set of tools. I'm calling them actions here, they're actions, and it chooses an action based on some policy. It chooses an action to do. The action will actually change the environment, and then some observer and interpreter will say, oh, okay, this is how the state now changed, and by the way, here's a reward for you for that, the selection of that action. So basically the agent doing that, trying different things, trying and checking the reward, it has an objective, is to maximize the reward it will get, and then it learns a policy that maximizes that. It's a little bit like a dog, teaching a dog to roll or give you the paw and things like that, and you give it a reward saying thank you or giving it a biscuit. It's the same kind of behavioral learning. And the pioneer in this technology is Rich Sutton, who is one of the faculty members in computing science and a fellow at the Alberta Machine Intelligence Institute. So here are examples of applications that we are working on here at U of A. People who lost a limb, a leg or an arm or a hand or whatever, you can bring them, you can give them these adaptive prosthetics. So we use reinforcement learning to adapt to the user rather than the user adapting to this new hook or new very static kind of prosthetic. These prosthetics can move and they can control them. And then the prosthetic can learn to predict what is the action that the user is about to do, and it can do it before even. So for example, I'm trying to grab a bottle in front of you, a cup in front of me. Instead of having this robotic movement, first I move this degree of freedom, then this one, then open my fist and then grab it. It's very robotic kind of thing. I can already open my fist and open my fingers as I'm moving towards the cup, because my prosthetic, my adaptive prosthetics, is predicting that I'm going to grab that. So it already starts opening the fingers, and then the movement becomes way more natural. And it becomes way easier also for the people who lost the limb to adapt also themselves to the prosthetic. It's not an easy thing to wear a prosthetic like this. So I think I covered my slides for today. I thank you for your attention. If you have questions, go ahead. I'll stop sharing my slides here so I can see you and you can see me.
Hi, I have a question. It's kind of silly, but how do you reward a computer? What does that look like?
First of all, it's not a silly question, and there are no silly questions. It's actually a good question. And it's a question that people ask all the time. What is the kind of reward you give to the computer? A child, you give it a sweet, you give it I don't know, a cookie, say, well, thank you, and a kiss, and I mean, something that they can feel is positive. A dog, same thing. You give it a biscuit. There is something material that you can say that's the reward. And if they're hungry, they will eat more and so forth. If it's sweet, they get that reward. A computer, you don't give it a biscuit. You don't give it a tap on the shoulder. That's not the reward that they want. So the reward is typically basically counter. It's a number. It's like being on a leaderboard. The more points I get, the better it is. So the objective is to get as many points as you can. And a negative reward would be a negative number. So I'm removing these numbers. I either increase it or remove it. And so to get the highest number possible, I will choose the actions that give me the biggest bonus. Does it make sense?
Yeah, that makes a lot of sense. Thank you.
Yeah, you're welcome. Any other question?
Yeah, I have a question.
Yeah, go ahead.
So I did write this in chat, but I'll just say it. So I've noticed, I guess not as like a decline of sorts in the development of genetic and evolutionary algorithms. I just don't see many new articles coming out, new research studies. I'm just wondering if it's, what you think the reason being would be. Like either it's like a fundamental flaw or the problem sets aren't appropriate to what we're using them for, or if it's just deep learning, reinforcement learning, overshadowing, like I guess the development and just, yeah, it's just not in the public eye. So I was just wondering what you think about that.
There are different schools. So it's not just genetic algorithms. There are also algorithms that try to mimic other behaviors of animals, like bee colonies, how bees collaborate to learn. So when you have a search space and you try to find the optimal solution, there are algorithms that are based on the behavior of ants or behavior of bees to go and scout, for example, the space and then communicate with the others in order to converge towards the solution. So these algorithms, as well as genetic algorithms, are are what we call optimization algorithms. They try to find an optimal solution in a big space of many possible solutions and try to avoid the local optimum, because you can fall very easily in a local optimum, how to get to the global optimum. They're still very good for some problems, but the progress is not as fast as what we observed with deep learning. So what we have observed with deep learning is phenomenal, that, as you said, it's overshadowing other things that exist. So the limelight right now is on deep learning. But it doesn't mean that the others are bad. It doesn't mean that these algorithms, nobody's working on them. There are some people working on them and they're still publishing on them, but it's not the same scale as what we have observed lately with deep learning.
Okay, thank you.
I had a question about, I don't know how to phrase it, but maybe the limitation of deep learning. So if you have infinite amount of data and infinite amount of time to just feed them into a machine learning algorithm, will you eventually end up with like intelligence, or is there something that's inherently limiting about them?
Well, there are many things that are limitations. So the most important limitation, and I mentioned it in the beginning, is the amount of energy that they require. So for example, they build a language model. I don't know if you heard of GPT-2 and recently also GPT-3. These are language models with millions and millions of nodes in this big neural network. And it cost them like $40 million to build. And the energy that they require is phenomenal. It's a waste. So many people are against them because of the waste of energy. You need actually energy also to cool them, to cool these computers running these models. So that's the biggest hurdle. And when you compare to the human brain that has way more connections, 90 billion connections, we use only 20 to 12 watts. It's nothing, barely a small light bulb. So that's one big issue. The other limitation is that we still don't know how we combine these architectures. So people are coming up with different architectures, but it's an art more than anything else. How the brain functions and how so when people are doing different actions, thinking about different things or trying to move a leg or trying to play chess, I'm not using my whole brain. I'm using parts of the brain, and how these functions are divided so that different parts of the brain are working on different things. We still don't know how to do that in neural networks. So we are limited on that. And I don't want to just make it big, even if I have, as you said, an unlimited memory. There's another issue, very important issue, explaining what happens in these connections. So there is a subfield in AI called now explainable AI. And explainable AI is trying to come up with the causes or the reasons for a particular prediction. So if I tell you this is a pen, and I asked you, why is it a pen? You'll say, oh, because it has a cup and I can write with it. It has ink inside. But if you show this to a neural network and you say, what is it? It may tell you it's a pen, yes, very accurately, because it saw enough pens. But if you say, why is it a pen? It's not able to answer you. So the reason will be, well, because I have these weights on these connections, it means nothing. So explainability is a big deal. Some people argue that we humans, we can come up with some also conclusions without being able to explain why. That is true. But for rudimentary things like this is a pen or and this is a phone, I can tell you why. I can explain. So deep learning is not able to explain yet things that they can predict. Anyways, there are still many limitations. So the power, the explanations, and the different architectures, and yeah, I hope I answered your question.
Yeah, that's interesting. Thank you.
You're welcome.
So Tian asks, why has there?
Oh, I think I already I
Okay.
asked that from chat. Yeah.
Okay.
I do have another question though, if I can. Okay. So, oh, sorry. Here, give me 1 minute.
Go ahead.
Okay, sorry. So I was wondering what your thoughts were on, I guess, the perils of AI. I feel like every year of my degree, I get more and more, less and less scared of AI and thinking of more of it as a black box that we use. Um, like AI not getting sentience to like overthrow humans, or like, like novel functions that will put us in danger. I don't know. It's harder the more I learn about AI, the harder it is for me to believe that it will stretch out of those bounds like that. I guess an example of it would be like social media. Like there's a lot of issues coming out with AI use in social media, but a lot of people would like to argue that's the humans, the input data that is causing all of these, like
Biases and stuff.
extremism in politics, for example.
Yeah,
So,
yeah.
yeah.
Well, we'll talk about this in the second, so on Thursday, about the perils. There are many perils, and people have been warning about the risks. And this is not new. They have been warning about these risks in the 50s and the 60s as well, when they believed that we could do this thinking machine. But the dangers also come from the humans, how we use these machines. Like one example is the killing robots. There's a huge movement, and I am one of the signatories of these petitions to petition governments, to ask governments not to use AI to weaponize AI, basically. But this is going forward anyway. So you will have machines that will make decisions to fire or not to fire on people. That's a big danger. It's actually more important danger than the danger of having a machine that thinks by itself and basically realizes, oh, we can pull the plug, so let's kill all the humans. What you can see in some science fiction movies. I think. Like you were saying, the more you learn about AI, the more you realize, well, that's not going to happen. At least it's not in my lifetime. But should we completely disregard it? That would be a mistake. I think we should talk about it and consider that this could be happening. And if it happens, what should we do to prevent it from happening? Even if it's not going to happen in the next year or the next decade, it'll happen after my lifetime. We should think about it today, think about the consequences and what we humans should do, not only to avoid it, but if it's unavoidable, what should we do? Now, there are things that may happen faster than we think. Like somebody has a new breakthrough realizing, oh, this is exactly how things are stored in memory. This is exactly how human brain is actually functioning, which we don't know yet. And then if we can implement it, then suddenly you have some form of intelligence that'll come out of this and self-awareness. That I don't know. I cannot predict. Nobody can predict that. If you look in the past, how we predicted the future, we are very lousy. I mean, just look at the old science fiction movies and you'll realize this is ridiculous. I mean, recently I also watched an old BBC video talking about computers in the 90s, and the guy at the end said, well, this we will not see it for a long time. They were wrong. There's a famous quote by the CEO of IBM saying, maybe we'll need 4 of these machines for humankind. And some other people were saying, how useful is this? I mean, we're always wrong at predicting the future. It is possible that in the next decade, somebody will come up with a bright idea to make machines really intelligent. That reinforces my recommendation to start thinking about it now and start discussing it now, thinking about the ethics of that rather than waiting till it happens. But as it stands today, we're still far away from these thinking machines.
Okay, thank you.
You're welcome.
I had a quick question about so one of the things that we've had in this course is quite a few when you talk about predictions about what AI will do in the future and kind of, trying to plot that sort of timeline. One of the things that I've kind of also heard about is the applicability of Moore's law in terms of circuitry density. Do you know if those models saying, oh, X will be obsolete in 15 years takes into account like the literal, I guess, physical space constraints of, circuitry separation, as well as, do we have enough resources to actually build these computers? Because, half the materials are only in China and there's a finite number of them, etc.
So Moore's law has been incredible. I mean, when it was predicted at that time, nobody thought that it will be going on and on and on for years and years and years. And each time it reaches its limits, people think, oh, that's it. Yeah, it was great. We had it so many years. Now it stops. And then the year after, boom, we do it again. Now we are reaching the atomic level and new technologies are invented. The speeds of the machines are going on and on and on. I mean, that doesn't stop. So I don't think that's, I'm not going to try to predict whether it'll stop or it will not stop. I'm optimistic that it'll continue to get better and better. And hopefully use less and less energy as well. So it's not just the space, it's also the consumption of energy, because when you cram everything in very small, they end up using way more energy and then you need to cool them down and it becomes way more complicated. Today, if you open a desktop, you will see all these fans and some are liquid cooled. But is that what will make machines think? Not necessarily. That's not the only component. The algorithm, how to use that hardware is also important. Hardware alone is not enough. You need the software to go with that. And we are very slow. We are slower at developing new algorithms compared to the speed at improving the hardware. Unless we can automate part of it, then things will change. And this is one of the things that can change the equation tomorrow. If we can automate some of this programming, suddenly we have something else. Did I address your question?
Yes, thank you.
Other questions?
I just have a really quick extension on what Alex said. I guess on like the end of Moore's law topic, because they're getting to the point where quantum tunneling has become an issue, hasn't that targeted like a very fundamental component to how computers have been working for the last like so many years? People are saying like, oh, maybe quantum computing is where we need to look for the next jump in performance. I'm just not sure currently what the plans are to deal with that issue of like getting so atomic that we are starting to get fundamental problems with operation.
So the two work together. That's why I said it's not just the hardware, but actually quantum computers are also a different kind of hardware using these qubits. Quantum computing are amazing machines. Currently, they are theoretical machines. Some companies are building some forms of these quantum computers. The Chinese, the Canadians, and the Americans, we have different architectures for these. But what is missing is how to program. We know how to program the traditional machines. It's not easy to program quantum computers. So they are working on one particular problem, and they work all these sophisticated programming for one problem. They're not versatile yet. They can't work on many different things. So we have many theories behind it, but in practice, we're still behind. This being said, there are many people who are working on machine learning with quantum computers. So AI with quantum computers, but it's not something that has been implemented. It's all theoretical at this point.
Okay.
All right. Well, thank you very, very much. Great teaching session. We'll see you on Thursday.
Yeah, Thursday. I was supposed to be in Europe, but I will still be in Edmonton. So
Okay. That's good for us. Okay, great. Thanks.
See you guys.
Thank you.